continuing on with our early discoveries in chemistry, and we're picking up with the discovery of electrons. And the way that they did this was using a piece of technology that was relatively new at the time, and eventually would go on to play a part in early televisions and early radio systems and things like that, and that is a thing called a cathode ray tube. All right, and it was invented by Michael Faraday. In 1868. Right, and at this point in time, they're still just learning about how to use electricity and in chemical systems, and not very long before this, electricity was really not much more than a novel sort of gimmick for parlor tricks and neat little gadgets. Not really even gadgets, but just for fun. But right around this time, they started discovering that electricity could be used to do science and actually make important discoveries. And so what you have is a glass tube, sort of looks like some of them look like sideways bottles. All right, I'm going to try and draw one here. Right, and at one end, let me use some different colors, that'll be helpful. On one end you have a metal band and another metal band. And what they do is they connect these two bands with a voltage source. So they start passing electricity from one to the other. And so one of them acts as a cathode, hence the cathode ray tube, and the other acts as an anode. Okay, sort of like the positive and negative ends on a battery, right? And so when they started doing this, what happens is the cathode pushes electrons, and at the time they didn't know they were electrons, but it pushes electrons toward the anode, and it creates a beam of electrons that goes to the far end of the bottle, and the far end of the bottle is coated with a photosensitive material. Okay, it responds to light. And what they found was when they hooked up this voltage source, they got a spot of light at the far end on the photosensitive material. But for all intents and purposes, this beam was invisible to the eye. Right, but they could see it at the far end when it hit the photosensitive material at the far end of the bottle. So the cathode ray tube emits radiation. Now they figured, well, all right, so this does a thing. So let's see what else we can do with it. Okay, so what they did was they started to play around with other aspects of what they could add to this cathode ray tube, and what they did was they stuck some magnets on each side of the tube. Right, so one positive side and one negative side. And when they did that, they found that their beam of light was attracted to the positive end. Right, so they were able to suppose that, I'm going to stick with the orange, some sort of negatively charged particle was being made. Okay, and not necessarily made. They didn't quite understand how things related to each other at the time, but these were the sort of terms that they were thinking in. So a little bit later on, there were more experiments that sort of showed exactly what that charge was and exactly how much an electron weighed. and all kinds of other wonderful experiments. But this was the first one that showed the existence of a negatively charged particle. So continuing on with our discoveries, the next one was the discovery of radioactivity. Okay, and it was initially supposed by Antoine Becquerel. Okay, and the Nobel Prize for the discovery and the verification of radioactivity went to, among others, Marie Curie. Okay, she and her husband and a few other scientists are all credited with the verification of radioactivity. That was Marie Curie's first Nobel Prize, by the way. She won a second one of the very, very, very few people in history ever to win more than one Nobel Prize, but she won a second one all by herself for the discovery of, I believe it was plutonium. To this day, Marie Curie's laboratory notebooks are too radioactive to handle without safety equipment. So she did a lot with radioactive stuff. But anyways, back to radioactivity. Antoine Becquerel, Marie Curie, and the other one that we want to talk about is Ernest Rutherford, very famous physicist of his day, and he identified individual particles of radioactivity. Identified alpha and beta radiation. Alpha and beta particles. Right? So alpha particles are basically a helium nucleus. Okay, but at the time they didn't quite understand that idea, but what they did know was that an alpha particle had 2 units of positive charge. And it had the same mass as a helium atom. Okay, so at this point in time, they still hadn't quite worked out what a nucleus was, or what a proton was, or anything like that. So they're just going on the idea that they know that this thing has 2 units of positive charge. And then beta particles are negatively charged. With about the same mass as an electron. Right. Later on, Paul Villard would discover gamma radiation, which is a type of electromagnetic radiation, and responsible for the Incredible Hulk, among others, and Captain America, and the list goes on and on. So the next really, really pivotal sort of discovery comes from an experiment that is very famous. It's called the gold foil experiment. Okay, and in order to understand the implications of the gold foil experiment, and this was, by the way, done by Rutherford again. He did a lot of good work for, he was a physicist, but boy, a lot of his discoveries were very, very important for chemistry. But Rutherford and his old pal, Geiger. And yes, that's the same Geiger from the Geiger counter. But what they did was they started with the idea of what's called the Plum pudding model. And this was the predominant idea at the time of what an atom was. All right, and the Plum pudding model basically says that you have a sphere of positive charge. Okay, the whole thing is positively charged. And interspersed within that positive charge are little units of negative charge that are the electrons. So they knew, they could verify that electrons existed. And what they also knew was that atoms were inherently electrically neutral. So they have the same amount of positive charge and the same amount of negative charge. But this was the idea. It was just sort of a blob of positive and negative charge. They didn't know what held it together. They didn't know why it had mass, any of that stuff. Okay, so working with this idea, the gold foil experiment makes an assumption that anything that is shot at that plum pudding model should fly right through. Right? So what they did was they took and they had the ability to send a beam of alpha particles. And I'm going to say A for alpha. Right? So if the plum pudding model is correct, that beam of alpha particles should fly straight through. And then on the other side of their sample, they have a wall of gold, not gold foil. Let me use a different color. They have a photosensitive material, sort of like what you'd find in a cathode ray tube. So you would be able to see where the alpha particle hit on the other side. Okay, and so why this is called the gold foil experiment is what they did was, let me erase all of this business, is that they had a sheet of very, very thin gold foil. Right? And that the idea was that if the atoms of the gold were like the plum pudding model, that should go straight on through. Okay? Well, what they found instead was that most of the alpha particles went straight on through, but a couple of them were deflected, and a couple of them bounced back entirely. Okay, now if the plum pudding model is correct, this should not be happening. But they did it over and over and over and over again, and they found that it happened every single time they ran the experiment. Some of the particles would get deflected off in an odd direction. Some would actually get bounced back in the same direction that they were shot off, okay, with some deflection in the process. So what this told them was that there had to be something solid in the atom. Right? If the atom is just a big blob of positive and negative charge, those particles should fly right through. But instead, there's something inside those atoms that is massive enough to deflect an alpha particle, which is basically the size of another atom. Right? So what this led to was the modern model of atoms. So the nuclear model. Okay, and the tenets of the nuclear model. First, most of the mass and all of the positive charge are in a nucleus. Okay. The other idea is that there is lots of empty space. In an atom. The next idea that goes along with this is that the amount of positive charge is different for different elements. And the last idea, and one that they sort of already knew, was that atoms are electrically neutral. In other words, they have the same amount of negative charge in the form of electrons. All right, so we went from this plum pudding model to the idea that there is a nucleus in an atom. And that number two, that lots of empty space. So to give you an idea really of how much empty space there is in an atom, if you can imagine the nucleus of an atom being the size of a baseball. Okay, and if you've ever been to a Major League Baseball stadium, let's say Busch Stadium, someday we'll be able to go back there. If you placed the baseball on the pitcher's mound, the nearest electron would be in the parking lot past the outfield wall. That's how much empty space is in an atom. Lots of it. All right, we're going to stop this video here. We'll come back talking about atomic numbers.